Okay, so last time we started our discussions on AC circuits, right? And then we first studied the behavior of a resistor in an AC circuit. Nothing special, nothing fancy. All you need to do is just find the voltage at that certain time, then just solve the circuit, like what we do with the DC circuit. Right? And of course, we introduce a new concept called average power, RMS values of the current and the voltage. So that's what we did with the resistors and an AC circuit. Inductors, they're more interesting than resistors. If you connect the inductor to an AC source with the same voltage function, cosine function, and then we used Kirchhoff's loop rule to solve for the function for the current, right? And we get this. This is going to be the complete solution. And then we define a few things so we can write it in a nicer way. Whatever this number is, that's going to be the maximum value this current can get. So I'm going to call this Imax. And then the Imax is defined as this, right? And then I realized that if I compare this equation with the resistance equation, Imax equals Vmax over R, whatever this is, this behaves like a resistance, right? And the unit for this guy is also going to be ohm, right? Because that's in order to make all the units right. So what we do is this: we're going to define this thing called XL, which the name for this guy is going to be reactance. Okay, excuse me. So this reactance, you can think of it as the equivalent resistance of an inductor in an AC circuit. So the inductor behaves like a resistor in an AC circuit. The difference is its resistance is equivalent resistance is calculated using this equation, but it depends on the source. If you connect it to a different source with a different angular frequency, this value can change. It's very interesting. So it just has like a varying resistance. And also, if you compare the current function with the voltage function, the current is always 90 degrees or 1/2 pi radians behind the current. And you can that is explained in this graph on slide 1, lecture 18, right? So you take a look at these two curves. The current always reaches the peak 90 degrees after the voltage has reached the peak. So that's what we mean by the inductor always makes the current behind the voltage 90 degrees or 1/2 pi radians. So they're out of phase. That's why we say that when a resistor is connected to an AC source, the current and the voltage, they're still in phase because they always reach the maximum at the same time, reaches the zero at the same time, reach the peak on the other side at the same time, okay? So inductors, similar to a resistor, but there are a few differences, okay? Now let's practice this current function we just derived and then the definitions. So this equation like this is also going to be given on a test, right? You don't need to remember this. And these definitions, right? Definitions, you don't need to remember that, right? So you will, we will have a lot of equations in this part, but most of the equations are going to be given on a test, like the definitions, the current function, the voltage function, okay? We don't need to memorize these equations. Now let's take a look at this question on slide 3. 25 microhenry inductor is connected to an AC source, okay? And the function is Vmax cosine this value. But in this case, it doesn't give us the Vmax, right? So it just tells us this is Vmax times cosine. It tells us the angular frequency, whatever in front of t. This is the angular frequency, right? This is the angular frequency omega. Okay, whatever in front of it. But we know that the current through the inductor has a peak value of 20 milliamps. Find the voltage in the inductor at t equals 6 microseconds. If I want to find a voltage at a specific time, all I need to do is just plug numbers in, right? Plug the time in, plug this in. But the problem doesn't tell us this. The problem says, I want you to find the voltage at 6 microseconds. Then what about the voltage? So the only thing I need to find is this Vmax. The problem doesn't tell us Vmax, but it tells us the current through the inductor has a peak value of 20 milliamps. It's telling us Imax. And Imax and Vmax, they're connected, right? Imax and Vmax, it's pretty much they're connected by Ohm's law, right? This is still Ohm's law, but this guy, we call reactance, but it's just like a resistance, okay? So all I need to do is this. Let's use the relation between the Imax and Vmax to find the Vmax, right? Because the problem tells us Imax, okay? And then this XL, it's omega times L. Everything has a definition, this part, okay? So if you rearrange this equation, you get Vmax equals Imax times this, and this is omega times L, right? XL, right? Then you can plug numbers in. What is omega? This is omega, 2 pi times 10 to the 5th radians. The unit is going to be radians per second. That's already in SI units. What is L? The problem tells us L is 25 microhenry. Okay, then you have all these numbers. Imax is 0.02 amp, right? Multiply them together, you get the Vmax. But that's only Vmax, right? Once you have Vmax, then I can use this function to find the voltage at any time. Just tell me which time, right? Tell me 6 microseconds, 5 microseconds, 10 microseconds. Okay, I'm just going to plug it in and tell you the voltage, okay? So do the math, okay? See if we can get the same answer. Okay, so then first you find this guy is going to be equal to 0.314 volts. Okay, so that's the Vmax. Then you plug it in. So what is the voltage at 6 microseconds? Well, you're just going to plug that number in, right? This is Vmax cosine 2 pi times 10 to the 5th. What is the time? 6 microseconds. Okay. This is how you find it. Again, remember, this must be in radians. When you calculate this number, you do cosine radians. The angle must be in radians, okay? Now you plug numbers in, you will get negative 0.25 volts. Okay, we got a negative number. Did we do anything wrong? No. To take a look at the function of the voltage, right? It goes like this. Negative number, because the voltage and current, they're changing direction all the time, right? When it goes this way, we call it positive, or goes that way, then we use negative sign to distinguish the direction, okay? Both the magnitude and direction are changing for the voltage and the current. That's why it's called AC, alternating current, okay? So there's nothing wrong. You will get you can get a negative number for voltage and current in this part, because that just means it's opposite to the positive direction you assume. It's just in the lower half of the graph on slide 1. Right, so that's voltage. Now let's do current, okay? Then current, that's just going to be that equation, right? IT, I just erased that. Imax cosine omega t minus 1/2 pi radians. Now let's see, do we have all the numbers I need to plug in this equation? Yeah, Imax, omega, that number, t is still the same, 6 microseconds. Don't forget this is negative 1/2 pi, right? Because it's always 1/2 pi radians below, behind the voltage, okay? You plug all the numbers in, I 6 microseconds, it's gonna be Again, use a calculator to do that. Put your calculator in radian mode when you cosine this thing. You will get negative 12 milliamp. Again, negative means it's in the negative direction. Whatever the negative direction assumed, right? It's in that direction. It's in the lower half of the graph. Okay, there's nothing wrong. You get a negative current of voltage in this part. So that's an inductor. Okay. Now let's replace it with a capacitor. Let's see how a capacitor behaves in an AC circuit. So slide 5. I'm going to erase this. Okay, so usually you will see I put a subscript L here because this is a current for inductor, right? Because we have different functions. Now let's work on the capacitor. So capacitor is this, right? The symbol is 2 vertical lines, parallel lines. It doesn't have to be vertical. Now the voltage is always this, right? Because that's the function we use for any voltage, AC voltage source. So that function doesn't change in this class. Now I want to again find expression for the current in this capacitor. Okay, how do I do that? You can use Ohm's law, but you can always use Kirchhoff's rules, right? So what I can do is this, like what I did with an inductor. I apply loop rule. There are only 2 voltages here. This guy has a voltage. This guy has a voltage delta VC, let's call it. And then let's plug them in. The voltage from the source is going to be Vmax cosine omega t, right? And this guy, it's going to be Q over C. If you still remember that, the voltage and charge capacitor equals charge over voltage, right? And if you want to find voltage, and then if you go this way, you will get a negative sign, okay? Because you're going down when you cross the capacitor, okay? Say at some point this is positive, this is negative, then this plate is positive, negative. You go this way, you're climbing up, but when you cross this, you're going down. So that's why you will get a negative sign. And then in this case, you don't even need to integrate anything, right? You just rewrite this equation, you will find the expression for charge, which is going to be C Vmax cosine omega t, right? So this is, but then wait, we don't want to find expression for Q, right? We want to find an expression for current. But current is defined as charge over time, right? Now you just take a derivative, dq over dt, right? If you take a derivative at the end, you will get this negative omega c v max sine omega t. Again, I want to replace this with cosine so I can compare the I function with the V function. If you do that, you will, like what we just did, you replace this sine function with, and then I want to incorporate this negative sign with that. So negative sine theta is going to be equal to cosine theta plus 90 degrees. So that's also an identity in trig. So if I use that, make use of that, then this becomes a very nice equation. Cosine omega t plus 1/2 pi. Right? So that's the function for the current. Now I'm going to rate this. I'm going to list it here. Okay? So again, I'm not going to ask you to derive this because in this part we're just going to apply this equation. So this is IC. It's going to be equal to omega c Vmax cosine omega t plus 1/2 pi. Excuse me. Now can you erase all this? So this is a nice equation I just found, which is the function for the time. So that means the current in the, there's also a current in this circuit, okay? So it's going to go back and forth, back and forth. Well, it's not going to cross the capacitors here, right? Because there's a gap here. But you're still going to see a current in this circuit. So it's very interesting. Okay, so capacitors and inductors, they're very interesting in AC circuits. More useful, more interesting than an DC circuit. Okay. Now, and then what I'm going to do is this. I'm going to still call this Imax, right? If I call this Imax, first of all, then you see that, okay, let's first do this. So this is a nice function, and then I'm just saying, just going to say Imax is defined as omega C Vmax. Then this is going to be the function I use for the current in the capacitor circuit, and you compare this with this. The function, cosine function, there's a plus 1/2 pi in this function, so that makes the current 90 degrees ahead of the voltage, right? If the voltage, this is 0, this is already 1/2 pi, right? If this is 1/2 pi, this is already pi. So it makes the current always 1/2 pi ahead of it, right? So take a look at the graph on slide 5, right? So the purple line is the current, always reaches the 0, 90 degrees before the voltage, reaches the peak 90 degrees before the voltage, reach the peak on the other side 90 degrees before that, right? So the purple line is always 90 degrees ahead of the green line. So we say that the current is always 90 degrees ahead of the voltage. So again, they're out of phase, but the capacitors is opposite to inductor. Inductor is going to make the current 90 degrees behind the voltage, and capacitor is like, it's going to make the current 90 degrees ahead of the voltage. So they're very interesting. They're very interesting. They're, these two guys. Okay, and then I still want to define something similar to XL. We defined the reactance, right? So what I'm going to do is this. I still want to write Imax like this, like the Imax equation I wrote for resistor, and the Imax equation I wrote for inductor, which has an XL at the bottom. So I'm going to write it as V max with something. So in this case, if I write it this way, I put 1 over omega C at the bottom, you divide them, you will get this, right? So I'm not changing anything, I'm just doing math. Now I'm going to call this guy XC. Okay, so XC is defined as 1 over omega C. And once you have all these definitions, you see that Imax equals Vmax divided by XC, which is pretty much like the equivalent resistance of a capacitor in the AC circuit, right? So you can still treat the capacitor like a resistor. The only difference is that the resistance, the equivalent resistance, which we call reactance, depends on the source. So it's changed. It doesn't have a fixed resistance. Okay, it depends on the omega, and we're gonna see this is very useful in real life. Okay, we're gonna see that later. Another difference, it's always gonna make the current 90 degrees ahead of the voltage, right? Okay, if you understand the inductor, then capacitor, it's very easy to understand. So this thing is still going to be in ohms, right? Because you see that this is still Ohm's law. I equals V divided by something. This thing has to be in ohms. Okay. All right, so that's the theory for capacitors. Okay, that's the theory for capacitors. Now again, let's practice this theory. So I want you to take a look at the question on slide 7. Slide 7. Capacitor is connected to an AC source. Okay, so this circuit, I'm going to erase all these numbers. What is the voltage we get? Still going to be this function, but what numbers do we get? 8 volts cosine omega t. In this problem, we don't know the angular frequency, but we know the Vmax, right? The frequency, the problem tells you the frequency is 5 kHz. Oh, so that means you can use the relation between omega and the frequency to find the angular frequency, right? So okay, so that equation, good. If you want me to find the voltage, I just plug numbers in. The reactance is 25 ohms. We want to find the capacitance of the capacitor. Okay, if I want to find the capacitance of the capacitor, so that's C, right? C is connected to the reactance, right? See, it tells me the reactance is 25 ohms. That's the XC. That's a name for that. And then all I need to do is just rearrange this equation to find the C, right? And what is the angular frequency I should plug in? That's 2 pi times this frequency, 5K converted. All right, again, pause the video, do this, and then compare your answer with mine. All right, so let's see. So first of all, I'm gonna rearrange that equation. XC equals 1 over omega C, right? You rearrange this equation, you get C equals 1 over omega times XC, right? And then omega is 2 pi F times XC. Now the problem already tells you XC equals 25 ohms. Now you plug it in, right? The frequency converted to 5,000 hertz. Okay, you plug numbers in, you can find the C is 1.27 times 10 to the negative 6 farad. Farad is that saying. So that's going to be B, right? B is the right answer. The capacitance of the capacitor, did you get the right answer? Now, the next part, question 8. Find the voltage in the capacitor. Okay, the voltage, we already have everything, right? 8 volts is the maximum value. 2 pi F is the frequency. Time, so it must tell you a time. 35 microseconds, okay? Put all the numbers in. Again, make sure you calculate it in radian mode, and then you will get the right answer. Okay, do the math. Alright, so that's how you're going to calculate the voltage, right? The function is there, everything's there. You can just, again, make sure the cosine function is in radians. Okay, what is the answer you got? 3.63 volts. Okay, so that's the voltage in the capacitor, because the whole voltage is in the capacitor, right? If you want me to find the voltage on the capacitor, that's just going to be the voltage from the source, right? Because it's not going anywhere else. It's all on the capacitor. Okay, the last part, slide 9. The current, find the current in the capacitor at this time. What is the equation for the current? This. Okay, so all I need to do is find this number, omega I already have, and then don't forget the 1/2 pi is going to make the current 90 degrees ahead of the voltage, right? Do we have Imax? We don't, but Imax is equal to Vmax divided by this reactance. Now it's like a resistance. Okay, so the Imax, I'm going to first do 8 volts divided by 25 ohms, right? So what is this number? Okay, 8 divided by 25. .32 amps. Now you can plug numbers in. I at 35 microseconds. It's going to be Imax times cosine function, this whole thing, plus 1/2 pi. That's the angle in this cosine function. Okay. Okay, and at the end you will get negative 0.29 amps. Right. So negative, did we do anything wrong? No, right? Negative means it's in the lower half of the graph, right? Because it goes like this, the current, okay? It will change direction all the time, okay? All right? So we have finished the capacitors. Now, what about this? So I've just learned the theory for resistor. Well, there's no theory for resistor, right? Because nothing special. The theory for inductor and capacitor. Inductor makes 90 degrees behind. Capacitors make the current 90 degrees ahead, right? Did I say it wrong? Inductors make the current 90 degrees behind. Capacitors make the current 90 degrees ahead, okay? So what if we put these three guys together in a circuit? So take a look at slide 10, okay? So that's called RLC circuit. You just put all these three things together in one circuit, okay? Now let's see. So this is gonna become really interesting. Now I'm gonna erase all this. RLC, three guys connected, okay? Doesn't matter how they're connected, they're just gonna be in series, right? So there's a R here, there's a L, and then there's a C, okay? And then let's first finish this theory, then we can see an application of this, right? Why we're doing this. We're not making our life hard because this is useful, okay? So I still have this. The voltage is this. Now I still want to find the function of the current, right? So this is pretty much like three elements to connect together. So everyone has their own role, okay? The resistor wants to make everything the same. The inductor wants to make the current behind. The capacitor wants to make the current ahead. So they're fighting each other. What is the net result? It totally depends on their values, right? So you can solve the current, okay? So we're not going to solve it here. You're still going to apply loop rule, right? Because there's one loop here, right? You apply loop rule, and there's only one current. If you want to find current in this circuit, there's only one current. They're still in series, right? So the function is here. It's this. It's still going to be a cosine function, right? Isn't it amazing? Okay. The same form. It's going to be I max times cosine omega t minus a phi angle. Okay, then what is I max and what is phi, right? I know that omega t comes from the source. They have a definition. So what is I max? I max is this. It's V max now divided by a thing we call impedance. Impedance, okay? What is this impedance? It's this. R squared plus XL minus XC squared. What is XL and XC? Well, we just defined them, right? XC is XL is omega times L. XC is the 1 over omega times C. They don't change. They're still the reactance from the inductor and the reactance from the capacitor. Okay? They don't change. Now, what is phi angle? Phi is this. It's called phase angle. It's tangent inverse of this value. All right? And then, okay? So it's actually when you solve this equation, you don't really get this, right? When you solve this equation, you get this. You get V max divided by this, cosine omega t minus this. You get a long equation, and we don't like that, right? We want to write it in a nicer form. Then, okay, I'm going to define I max this way. I'm going to call this angle phi, so that I don't need to write a long solution. I will just write this and tell you what each term is. So it's so nice, right? It's not like when you solve, you get a nice equation like this, and then someone told you, hey, define this, define that. No. When you solve it, you get a very long equation. And then we don't like that. So we define things. Because whatever in front of this cosine function is going to be the maximum value the current can get. So I get this divided by this. I'm just going to call it Imax. And this whole thing down here will behave like a resistance. It's pretty much like the equivalent resistance of these three guys combined. So that's why I'm going to call it Z. The symbol doesn't really matter. You can use whatever symbol you like, right? And we call it the name impedance, right? And this phi angle, you have omega t minus this whole thing here. Okay, I don't want to write it there. I'm just going to define, I call it phi, and then phi is this angle. Okay? So when you see an AC RLC circuit, you have a lot of definitions, right? These definitions are going to be given, right? You don't need to remember this. So on the final test, you will get a lot of equations. You never need to worry about equations in physics in my class, okay? So the only thing is that you just need to plug in numbers into these definitions, find everything carefully, and then do the algebra, usually, okay? This part, we have a lot of definitions, but the problem we have solved are mostly just plug-ins, right? Okay? So that's the current. The current is easy, because there's only one current. Then what about the voltage on each guy, okay? The voltage in each guy, let's see. The voltage is going to be this. So first of all, how do you find the voltage on resistor? Voltage on resistor, that's easy. I can just do I times R, right? Because for a resistor, you can still use Ohm's law, right? It doesn't matter how many elements are connected to this. If I know the current through this guy, I multiply the current by the resistance, I get the voltage. The current is a function, fine. The voltage is also a function, right? So that means that this guy is going to be Imax. Just multiply that function with R, right? R times cosine omega t minus phi. Very easy, okay? Once you have the current, you can find the voltage for the resistor very easy. What about the voltage for the inductor capacitance, okay? You can still figure it out, okay? Because we learned that if there's a one resistor, capacitor, inductor, connected to the voltage source, you get this. You get this equals Vmax over R cosine omega t minus this. And then if you get a capacitor, right, you will have this Vmax. No, this is not R, I'm sorry. This is XL. This is V max over XC, then cosine omega t plus this, right? So these two equations are also going to be given on the test. You don't remember that, okay? Now the key is this. I want you to do this. Use these two theories to figure out the voltage for the capacitor and the inductor. How do I figure that out? Let's take a look at the inductor. If I want to find the voltage for the inductor, so this is not going to be given. This is something you need to figure out, okay? Again, if you understand that, it's easy. If you don't understand that, you have to memorize everything, okay? First of all, it's got to be something like this. It's got to be Vmax, okay? Something maximum value times a cosine function. Because everything is going to be like that, right? Then how do I figure out this and this? The maximum value for this voltage on the inductor, okay, it's going to be similar to this because the XL and then these Vmax and Imax, they're connected, right? Because you're going to put the Vmax for this inductor here. But for an inductor, Vmax is always equal to, for inductor, because Imax equals Vmax over XL. That's only for one inductor connected, right? So if I want to find a Vmax for the inductor, which is not this Vmax, because this V is on three of them, I would just do Imax times XL. That's going to be the maximum value for the inductor, the voltage on the inductor, right? And then what about the cosine function? The cosine function, I already have the function for IT, okay? What is the difference between the current of voltage and inductor, okay? The relation is this. The current from this theory, if I see this theory, the current is always going to be 90 degrees behind the voltage. But now if I tell you the current through the inductor, how do you find the function for the voltage? Okay? You understand my question? Okay, don't fall asleep. This needs some thinking. I already learned that if I connect the one inductor to the source, I will get the current always 90 degrees behind the voltage. But now I'm going to apply that in this circuit. I'm doing things backwards because I already have the function for the current. It's going to be cosine omega t minus phi. If you have this function, how do you figure out the function for the voltage on the inductor? Then the voltage is going to be 90 degrees ahead of the current. Remember what we learned? The current on the inductor is always going to be 90 degrees behind the voltage. So that voltage will always be 90 degrees ahead of the current. Now I have the function for the current. How do you figure out the function for the voltage? It's going to be whatever this function is, I'm going to add 1/2 pi to it. Because now I'm going from current to voltage. Okay? If you're going from voltage to current, you're going to minus 90 degrees. Now if I go from current to voltage, I will get this function. So that's how I figure out the voltage for an inductor. Now capacitor. Let's use the same method. What did we learn about capacitor? If I connect a capacitor to an AC source, the capacitor always makes the current 90 degrees ahead of the voltage. So the current in the capacitor is always 90 degrees ahead of the voltage. So that means the voltage in the capacitor is always going to be 90 degrees behind its current. Okay? So this guy is still going to be some value, maximum value times the cosine function. The maximum value, that's easy. It's going to be similar to this, right? Because the maximum voltage is always going to be Imax times XC. That's a relation between Imax, Vmax, and this XC and XL we define. What is this function? Current is always 90 degrees ahead of voltage. So voltage must be 90 degrees behind the current, right? So I already have the function for the current in the RLC circuit. I'm using that theory in this new circuit, okay? So the current already has a function omega t minus phi. That's the first thing I derived in this circuit. Now I want to use that function to find the function for the voltage on the capacitor. Capacitor, voltage, current 90 degrees ahead. So voltage is going to be 90 degrees behind the current. Current, now I'm going to subtract 1/2 pi. Okay? Because now you're doing things backwards. Okay? This is not confusing. Don't tell me this is confusing. This is not confusing. It's math. Okay? You do math, you get the right answer. Okay? Because you don't know how to work with these guys intuitively. You never do, right? Because this is something you don't have direct experience with. So you will get all these equations. You see that you will get all these equations, all these definitions, right? But these two equations, I'm not going to give you them. Okay? You need to know how to figure out these three voltages. If you understand the theory, which is what we do in physics, you don't need to memorize these equations. You use the theory, you can figure them out on a test, right? If you don't understand theory, you always need to remember a lot of things. Okay? So that's what we're learning. In RLC circuit, you will get this, and I want you to use the theory for 1L, 1C to figure out these three voltages. This is easy, right? You just do Ohm's law if you have the current. Now these two guys, you're going to figure out the maximum. You're going to figure out if you're going to add 90 degrees or subtract 90 degrees. Use this theory. You just go backwards. you can always figure it out. Okay, so now this is RLC circuit, and then the rest is just going to be plug numbers in. Okay, so we're going to practice a problem next time, because because this is going to be a long problem, so I'm going to do the next time. Okay, I'm going to stop here for this video.